You'll be speaking English?
Is it okay to speak in English?
Yeah, maybe. You know, in principle, some lectures will be in English, some lectures will be in Russian. So, but I guess all of you, to some extent, know English, and that's not really a problem.
Let's walk.
Yeah.
Okay. Let me try also to ask you, can you hear me without a microphone? Probably you can hear. I think microphone will not help me to handle the blackboard. Okay, so it's a great pleasure to be the first lecturer at the first summer school of the newly founded foundation basis, and I would like to thank all the organizers and also the founder of this foundation for inviting me to talk at this school. So I will be talking about quantum field theory, and let me make a statement from the very beginning that quantum field theory, in my opinion, and not only in my opinion, is one of the greatest achievement of theoretical physics in 20th century. So quantum field theory arose, as you might know, from an attempt to merge two already existing and experimentally verified theories: quantum mechanics and the theory of special relativity. And today we know that quantum field theory stands under precision tests in numerous colliding experiments, for instance, in the Large Hadron Collider at CERN and also in Fermi Lab in the USA. And I also should point out right away that quantum field theory has a universal character. The methods of quantum field theory are universal, and they are applicable not only to theory of elementary particles, but also, for instance, for theoretical condensed matter. That's why it's very important to understand basic principles and basic ideas about quantum fields. And so I see my role in this school as to introduce you some basic concepts of quantum field theory. And today is the first lecture, and I would like to talk about symmetries in classical field theory and symmetries in quantum field theory. So symmetries. Why symmetries are important? Symmetries are important because the nature is very gratifying to us, in a sense that if you know the laws of nature at one point of space-time, then you know them also in the other point of space-time. So the laws of nature are not random from point to point. They are related. Also, if you have the laws of nature at one point and in one direction, then you can look in the other direction, also ask the question if the laws of nature are the same in a different direction or they are different. And as I told you, the nature is such that if you know the laws in one point, then you know them at any other. And that is essentially what is the role of symmetries in our world. Now, in order to set up the discussion, I need to tell you some basic things about classical fields, and let me probably start from mentioning that in classical field theory, we start from the description of a theory in terms of actions. Let me see. How can I use the blackboard? So I need all the blackboards which you have here. So let me take this one here, and let me also take this one. Okay, so this is for the chalk, right? And this is for the marks. Very good. So let's see. So we start from the action principle. So if we have a dynamical system which essentially is described by a set of fields, I denote them collectively by the letter phi with an index I. And I assume that these fields depend on a point x, where x will be the space-time point. And then the action, which describes a dynamical system, will always be assumed to be an integral. In general, let's assume that we consider our fields in d dimensions. So differential dx will be understood as a product of differentials dx0, dx1, and so on up to dx d minus 1. Integral over the space-time of a Lagrangian density, which I denote by L, and this Lagrangian density is assumed to be a local function of fields phi ix and of their first space-time derivatives. Now, from the action principle, which is a principle of the least action, or Maupertuis principle, if you wish, you can find equations of motion which describes the dynamical evolution of the system. So for that, you need to find the variational derivative of the action with respect to the fields. And if you vary this quantity here and you drop the boundary terms, you will find the following equation. Variational derivative, or this is a normal derivative of the Lagrangian density over the fields minus derivative mu derivative of the Lagrangian with respect to mu phi I on x equals to 0. And these are the fundamental equations which are known under the name the Euler-Lagrange equations. So this is a starting point, Euler-Lagrange equations. This will be our starting point to discuss the formalism of classical field theory and later on Any questions here? Is it what I'm saying very unusual to you, or you have seen that? So basically, this description of the theory is a description of a mechanical system, if you wish, with infinite number of degrees of freedom. The infinite number of degrees of freedom is comprised by this field phi x, and x here can be understood as a label. And since x is continuous, you deal essentially with infinite number of degrees of freedom labeled by this variable x. So raise your hand who understands what I'm talking about here. Perfect. Very good.
Gleb, excuse me. How important is those assumptions that you drop out all these full derivative terms?
Yeah, I will say it in a moment. This is what I'm trying, what I will be talking now about. So, if you change the Lagrangian by adding to it the total derivative term, like this one, then it appears that the Euler-Lagrange equations, which derived from this new Lagrangian, do not change. You change the Lagrangian by the total derivative, but the equations of motion will not change. So here, let me assume, it's very easy to show that this is indeed the case. So let me assume that my variable lambda mu is a function of the fields phi I only, That is because I don't want to change the nature of my Lagrangian. I assume that my Lagrangian contains only first derivatives of the field phi I, and this is simplifies my discussion because I would like to discuss only unitary theories, and for unitary theories, Lagrangian typically depends only on the first derivative of the field. So in order not to destroy this nature of the Lagrangian to depend only on the first derivative, I will assume that this addition lambda also depends on the field phi I. Now, if you continue a little bit this equation here, so if you write down explicitly this derivative as a derivative of the composite function, so you write this equation like derivative of the Lagrangian with respect to the field phi, let's say phi j, second derivative d mu phi I, like this. D mu phi j minus second derivative of Lagrangian with respect to d phi j mu d mu phi I d nu phi j. Then this is an explicit, if you wish, very explicit form of the equations of motion. So what I have done, I just differentiate this function here as a composite function. So this Lagrangian density here is a function of the field and its derivative. And so this is what I have done here. I differentiate Lagrangian first with respect to the field, and then field with respect to space-time point. And here I differentiate Lagrangian with respect to derivative of the field, and then derivative of the field with respect to the space-time point. So explicitly, Euler-Lagrange equation, you see that this is nothing else as a partial nonlinear differential equation. And so essentially, a lot depends on our ability to solve such kind of equations, partial nonlinear differential equations. Unfortunately, our mathematical colleagues are not so far with solving the general problems of this type. Typically, partial nonlinear differential equations are very, very complicated, and we don't know how to find general solutions. In any way, we continue first with this concept of the Euler-Lagrange equations, and
I'm sorry, wasn't that Israel Gelfand's remark that partial differential equations are beautiful?
They are beautiful
for the reason that they are not solvable in general.
Yeah. I can add to this statement that among that equations, of course, there is a set of equations which you can solve exactly, and that leads to the notion of integrability, integrable models, and so on and so forth. But in general, in quantum field theory, unfortunately, we don't know much about how to solve such equations. In any case, people found an ingenious way how to overcome this problem, and not really to concentrate on the partial differential equation, but go away and build up the formalism of quantum field theory without stopping at this point here. Anyhow, my statement is that if you now substitute in this equation here, instead of Lagrangian L, you substitute the quantity d mu lambda mu, so you replace L by d mu lambda mu, then you can check that this quantity here will turn out to 0 automatically. Just make this is a little exercise, we can do it in exercise class. So you will write this expression here also as a derivative of the composite function. So you differentiate it with respect to the field phi, and then you differentiate phi with respect to the space-time point. Then you take this expression here, substitute it instead of substitute instead of L here, and we will see that this left-hand side will be automatically satisfied. It will turn into 0 identically. Good. So this is a Lagrangian, Euler-Lagrange equations, and this is all what I need in order to discuss, in order to approach the description of symmetries in classical field theory. Now, the topic which I would like to discuss now is the so-called the first Noether's theory. Noether's first theory. In general, even if we would be able to solve such partial linear equations, then we will not get the full description of the theory. Because in addition to these equations and its solutions, what we would like to know, we would like also to know the so-called dynamical invariance. Dynamical invariance are the quantities which stay intact during the time evolution of the system. In other words, dynamical invariance are quantities which are conservation laws. So dynamics is non-trivial. Fields somehow develop in time. They undergo non-trivial evolution according to this dynamical equation. But there are some quantities which are constructed in terms of these field variables, field phi I and its derivatives, such that during the time evolution, these quantities remain to be the same. Do you know examples of such quantities? Conservation laws? Energy? Something else? Momentum? Yes. Yes. So this is typical examples of dynamical invariance. Energy, momentum. For instance, you know that momentum, conservation of the momentum is related to the fact that your system exhibits invariance with respect to the space-time translations. And this is something which I started my lecture with. I told you that the laws of nature are translationally invariant. If you have them here, you can translate your system and you will find them in the other point to be the same. Energy describes the invariance with respect to time, with respect to the shift of time. So if you make an experiment at this point, and then you make the same experiment in hundreds of years with the same initial conditions, you will find the same result. And this is precisely what conservation of energy is responsible for. So energy and momentum. And already from this very simple discussion of, so to speak, school examples of conservation laws, conservation of energy and momentum, you see that there is a very interesting relation between symmetries, between translational invariance with respect to space and time, and between conservation laws. So symmetries imply conservation laws. And this is essential point of the Noether's theorem. Symmetries imply conservation laws. Of course, these fundamental conservation laws, like conservation of energy and momentum, they were discovered long time before M.S. Noether's first theorem, which actually was formulated first in 1918 by M.E. Noether. But Noether understood how to apply, how to describe this relationship between symmetries and conservation laws in the context of field theory and in a precise mathematical language. And now what I will do, I will give you a formulation of the first Noether theorem, and then I will prove this theorem. And I think this is a first fundamental point which you would like to understand when you start to study quantum field theory. So first Noether theorem is formulated in this way. To any S-parametric continuous transformation of fields and space-time coordinates for any S-parametric continuous transformation of fields and space-time coordinates, there exist exactly as dynamical invariants. Where dynamical means that these quantities remain the same under the time evolution. So they do depend on the dynamical variables, but they are the same. So dynamical invariants are for me the same as conservation loss. These are synonym. And that's I have not yet finished. Sorry, I have not yet finished with the formulation. Let me finish, and then I will explain all what is in here. To any S-parametric continuous transformation of fields and space-time coordinates, which that is important, leave the action as invariant, possibly up to boundary term, there exists S conservation loss. Let's make it simple. S conservation loss. Some people use the word dynamical invariant, some people use conservation loss, but they are synonymous for me. So basically, this theorem tells the following. So there is a symmetry, or almost symmetry, of the action, which depends on S parameters in a continuous way. So you can make continuous transformations of your action, continuous transformation of your fields and space-time coordinates. And if these transformations leave your action invariant, possibly up to the appearance of the boundary term, like this one, then you can derive from the statement that there are S conservation loss. And now I'm going to sketch you a proof of this statement. So first of all, the transformation which I'm talking about is a transformation which might transform the space-time points. So x goes to some new point x prime. And also field phi I x goes to some phi I prime on x prime. And accordingly to these transformations...
Is that the transformations from a group, or they can be arbitrary?
No, they will form for me a group. In my discussion, they will form a group. But I'm working here at the... You will see in a second. Yeah. So x goes to x prime, phi I transforms in this way, and also derivative d mu phi I on x goes to d mu prime, it's a derivative with respect to x prime, to phi I prime on x prime. So this is the transformations I'm talking about. And if under this transformation the action S or the corresponding Lagrangian density is allowed to maximally change by changing by total derivative term like this one, then there will be S dynamical invariants. And in order to prove this theorem, I will do the infinitesimal analysis. Is it maybe
this one?
This one. This one is better. This one is probably not good. Yeah, this is. It has a lot of memory somehow. Okay, so what is meant here by invariance, let me write it explicitly, is that now you have an integral under the change of coordinates and the fields. The action takes the form dx prime of Lagrangian, depending now on phi prime I and d mu phi prime should be equal to dx Lagrangian, original Lagrangian, phi I, d mu phi I, no, maybe by also changing by the boundary term. In the original Noether theorem, I should point out the possibility of having this boundary term was not noticed, but later on the student of Emmy Noether, Bessel Hagen, noticed this fact in 1922, that the Noether theorem can be generalized by allowing the corresponding Lagrangian density to be changed by the total derivative. So it's a small generalization of the original Noether theorem, is the possibility to have this non-trivial boundary term. Anyhow,
but the Lagrangian there is the same number, not lambda prime.
It's actually lambda prime. It's everything
lambda
is prime.
prime.
It's everything is prime here. Thank you. Yes, everything is prime. Good. So let me see how we go with the proof. So consider infinitesimal change, which corresponds to this transformation here. So let's write x prime to be equal to let's x prime mu to be equal x mu plus delta x mu. Delta x mu is a small change, and we also assume that we parameterize delta x mu with these s parameters, namely we write it as sum x mu n epsilon n, and n is running from 1 to s. So epsilon and here are parameters of the transformation. These are parameters of the transformation, and these variables x capital, these are not this little x, but these are variables which I write as x capital, and they do depend on two indices, on index mu of x and also on this extra index n related to this epsilon n parameters. And analogously also for the fields, delta phi I is delta phi I on x. We assume that this variation is also parameterized by these parameters epsilon n, and the coefficients phi capital here, not little one but capital, depending also on two indices I and n, epsilon n. So in general, these objects here, x and mu and phi I n, are functions, definite functions, which specify the transformations we are discussing. These are definite functions of fields and coordinates. Fields and coordinates. And parameters epsilon n, they are constants, and in a sense that they do not depend on the space-time point. So just constants, arbitrary constants. And you see from these expressions that transformations delta x mu and delta phi continuously depend on these s parameters epsilon. Now, consider the variation phi prime I on x prime. And we can write it in the following way. Phi prime, and instead of x prime, I substitute x plus delta x like this. And then I will expand this expression here into Taylor series, assuming that delta x is small, and I restrict myself just to the leading term. So this will be phi prime I on x plus d mu phi prime I on x delta x mu, and essentially plus dot dot dot, which is phi I prime on x plus d mu phi I on x x n x capital n mu multiplied by epsilon n plus dot dot dot. So here I allowed myself to draw prime because the difference between phi and phi prime is of order epsilon, so this term would be the correction to this term, better to say the difference between this term here and this one without prime is of order epsilon squared. So I put it somewhere here, dots, 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 which I'm not interested in. And an important quantity which I would like to define now is the so-called variation of the form of the field, which I denote not by the usual delta, by delta with a bar. And I will explain in a moment why this quantity is useful. And this quantity will denote the difference between phi I prime on x minus phi I on x. So the point is that this variation delta, which is actually introduced here as, let me define it, let me first give a definition. This is a difference between phi I prime on x prime minus phi I on x. This is by definition the quantity here. This variation delta does not commute with the derivative d over dx. And this is for the reason that this variation here happens because you not only vary the form of the field like here, but you also change the space-time point. You change from x to x prime. And so the difference between these two, variation delta, this is something which does not commute with d over dx because it's not clear over which variable, for instance, you have to differentiate this expression over x prime. It's not clear. Well, here for the variation of the form, it's clear. The right-hand side depends only on the point x, and you can first differentiate then vary, or you can first vary and then differentiate. So delta bar operation here commutes with the space-time derivative d. Now, good. With these definitions here, you can actually compute what this variation equals to, because here, on the left-hand side, you see phi prime on x prime. On the right-hand side, you see phi prime on x. And this is according to, if I subtract from here, okay, let me maybe write it here. So phi prime I on x prime minus phi I on x. This is by definition is delta phi I. And on the other hand, this gives me the difference between phi prime on x and phi I, which is a variation delta bar phi I on x plus d mu phi I x mu n epsilon n. And this is parameterized by this expression here, which I can substitute to the left-hand side and express, therefore, this operation delta bar acting on phi I as the following quantity. So this is phi capital I n minus d mu phi I little x mu n epsilon n. I always, let me not to write dot dot dot, I'm always restricting myself just to the leading order in upset. Okay, so this is an explicit expression for this operation delta bar. Any questions here? So what I'm trying to do, let me explain the basic idea. What I'm trying to do, I'm now trying to set up this variational problem. And actually what I want to do, I want to compute the difference between the left-hand side and the right-hand side. You see, it's very interesting, yeah? The right-hand side is collapsing a little bit. In the left-hand side, what I would like to do, I would like actually to replace all primes quantities with unprimed ones by using the expressions for the corresponding variations. So this is my goal. And on this way, I will derive explicitly the expressions for these conserved quantities. Okay, let me continue here. Okay, yeah. I think I should use probably another one, another marker. Because this is full black, maybe I will use another one. Use a little black stuff. The red one is better. So now we come, let's look now at this expression here, the left-hand side. So we have L prime Lagrangian density computed on the prime fields, but altogether this expression is nothing else as lambda prime on x prime, because our prime fields are functions of x prime. So it's okay. I will use the red one, maybe it's better. Let me try. So L prime yeah. Yeah, I will try this one. This goes better. Okay, so let me do this one. And we continue to write. So this is lambda prime, again, x plus delta x. This is lambda L prime on x plus d mu L delta x mu plus dot dot dot. And this I will write as L on x plus L prime on x minus L on x. So I added and subtracted the Lagrangian density plus d mu L delta x mu plus dot. And this expression here is, according to my definitions, is nothing else as delta bar applied to x. Good. So this is what we do with the transformed Lagrangian. And then there is also here the measure, integration measure, which is now changed because it's now d on x prime. And in order to understand how it's transformed, let me do a change of coordinates. So I go from x prime to x. And as you know, the differential then changes as you have a Jacobian, j multiplied by dx, and the Jacobian here is determinant of dx prime over dx matrix. And to understand how this determinant looks like, let me write this matrix quite explicitly. So it has the following matrix elements: dx 0, d minus 1 over dx 0, and here dx prime 0 over dx d minus 1 dot 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 dx prime d minus 1 over dx d minus 1 multiplied by dx. Okay, so this is a determinant of such a matrix, which is a matrix of dx prime over dx. So this is just a change of integration measure according to the standard rule. Actually, I have to put modulus of the Jacobian, but you will see that since I'm computing infinitesimal transformation, this Jacobian is close to identity, so it will always be positive in this respect. So now, if I substitute this expression for x prime as original x plus small variation delta x, then this matrix turns explicitly into the following one. So determinant of 1 plus derivative of delta x 0 over delta x 0 dot 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 1 plus derivative delta x d minus 1 over dx d minus 1. And the matrix elements which are standing outside the main diagonal, these all elements are certainly of order of epsilon. For instance, if you look at this element here, it will be derivative delta x 0 over delta x d, and variation of delta x0 starts from x0, so the leading term is 0, not 1 as here, as on the diagonal, but it's 0. So if you now would like to evaluate this determinant up to the first order in epsilon, actually contribution to the first order in epsilon will be provided only by the main diagonal. And this will be given by the following expression. So if I restrict myself to the terms of order epsilon, they will give me just divergence d mu delta x mu dx plus dot dot dot, which I'm not interested in. So this is how the integration measure looks or changes up to the leading order in the deformation parameter epsilon, in this transformation parameter epsilon. So this is of order or capital 1 epsilon. Good. Now I can combine all the pieces of this analysis together and write an explicit expression for the left-hand side of assumed equality. Okay. So what do we have? I will be a little bit slower, so you will see all my steps. So first of all, let me not to transform the measure, let me just substitute L prime. And L prime is given by this expression here. So original Lagrangian L plus variation of the form of the Lagrangian plus d mu of L delta x mu. And that is all what we have at the leading order. And then I have to substitute here the, okay, let me write approximately. I substitute here the expression for the change of the measure. This is how the measure changes, and I multiply it by what I already have. And what I do, I again perform a multiplication here and leave only the terms of maximally order epsilon. So this will give me the following thing. So first of all, 1 multiplied by Lagrangian gives me original Lagrangian. Then this expression here is of order epsilon, so I don't need to multiply it by these two terms, which are already of order epsilon, because they are variations. and therefore contribution will be given by the product of this term by the original Lagrangian. And 1 will multiply the rest. So I will get delta bar L plus G mu L delta X mu plus L multiplied by d mu delta X mu. That is all what I have at the leading order in epsilon. And then you see that magically things combine a bit, and I get here the derivative d mu applied to the product. Lagrangian multiplied by delta X mu. So these two terms are combined now. You see that they are combined into a one derivative. D mu applied to a Lagrangian density multiplied by delta X mu. And the next step, what I will do, I will compute the variation of the Lagrangian. So variation of the Lagrangian happens because variation of the form of the Lagrangian happens because the Lagrangian depends on the fields, and fields change their form. So I can compute this variation as a variation of the composite function. So first I differentiate my Lagrangian with respect to field, and then I apply variation of the form to the field. And also what I will do, I then add derivative of the Lagrangian with respect to the derivative of the field. And as I already told you, a variation of the form does commute with the space-time derivative. So here I can change the derivative and the variation. So derivative acting on the variation of the field. And one little step is to rewrite this term here as in the following way. So I will write it as a minus d mu acting on dl d mu phi I delta bar phi I plus derivative d mu acting on the product of d mu phi I delta bar phi I. You see, this is an identity. If you open up this derivative, then when derivative acts on the first term here, it will cancel with this term, and then derivative acting on the second term on delta bar phi I gives me an expression which I already have. So this is just an identical transformation. But in fact here, you see that this delta bar phi I is an overall for these two terms and can be taken out of the brackets. I can write the expression in this way. And actually, in this expression here, you recognize the left-hand side of the Euler-Lagrange equations. So this is an expression which I would like to call Lagrangian derivative, epsilon I. For Euler-Lagrange equations, if they are satisfied, then this Lagrangian derivative must be equal to 0. But let me not to put it to 0, it's just some expression which turns to 0 if equations of motion are satisfied. In general, it is there, and therefore I'm obtaining the following statement that change. So this is my original action, or let me write it as a. Here it's actually this is S prime action which is obtained after I change my fields. So S prime turns into the following expression. So S prime becomes given by integral dx original Lagrangian. But let me write and probably an expression right away for delta S. And delta S is the difference between S prime and the original S. So this integral here is an original S. So delta S by definition is S prime minus S. So when I take this difference, Lagrangian, the leading term, here, which is Lagrangian, it will just cancel out. It will cancel out, and then what I will find is here Lagrangian derivative multiplied by delta bar by I plus derivative d mu acting on this term here, and in addition I have this derivative here. So altogether this will give me a total derivative of the following term. Like this, delta bar by I plus Lagrangian multiplied by delta x. And then the bracket is closed. So this is our intermediate result. Now, what we allow in the Denotes theorem, the difference between the left side and the right hand side, could be just an integral of the total derivative of some vector lambda mu. So this is d mu lambda mu. And therefore, on the one hand, we computed this variation, it is given by this expression. On the other hand, it is given by integral of dx of d mu lambda mu. And these two, by assumption of the Denotes theorem, must coincide. If we are talking about the symmetry of the action, that precisely means that these two coincide, and so I subtract one from the other, and I obtain the following statement. 0 is equal to integral dx epsilon I delta bar by I plus d mu by I delta bar by I plus Lagrangian delta x mu minus lambda mu. Integral, such an integral must be equal to 0. And let me close the bracket. Okay. So this is a result of our variational analysis. Now I should point out that when you consider the Denotes theorem, the integration volume here is assumed to be arbitrary. And so the vanishing of this integral for arbitrary volume omega, for arbitrary integration volume, can be only possible if the integrand which you integrate is 0 by itself. For arbitrary volume, that is possible only if the integral is equal to 0. And this gives the statement that there exists such a differential relation. There exists such a differential relation. This is differential relation which involves variations of the form of the field by I and the variations of the coordinates delta x mu. And the final step of the Denotes theorem, when it says Dirac S conservation loss, it means that these objects, that these dynamical invariants, or these conserved quantities, they are conserved provided Euler-Lagrange equations are satisfied. And that means that if the Euler-Lagrange equations are satisfied, this expression is valid all the time. But if the Lagrangian equations are satisfied, then this term is absent, because what is written down here is a Lagrangian derivative, which is the left-hand side of the Euler-Lagrange equations. So if the Euler-Lagrangian equations are satisfied, we get a statement that there exists an object. Let me call this object J mu, such that on equations of motion is actually a current J mu. On equations of motion, this current is divergenceless. It has no divergence. So divergence of this current vanishes. Mu J mu is equal to 0. And finally, if you now substitute here an explicit form for the variation delta bar phi I, and also for delta x mu, where the functions x capital and phi capital, and you use the effect that all the parameters epsilon n are independent. So you can actually write this current as J mu n epsilon n. Then this equation, since all epsilon n are independent, they will be valid for any n separately. And if I allow myself to continue this blackboard, I will give you an explicit and final expression for these currents. J mu n are given by. I will put an overall minus sign in front of this expression. This is a historical. This is put there for historical reasons. So derivative of the Lagrangian phi I n minus d nu phi I x capital mu n minus Lagrangian x mu n plus lambda mu n. So this is an explicit expression for current corresponds to this index n or corresponding to this parameter epsilon n. And for any n, there is a local conservation law which reads like a statement that the corresponding current is divergenceless. And actually, this is an explicit expression. So if you know how your symmetry transformation looks like, if you know what transformation you are talking about, then you can identify what is f capital, what is x capital, you know your Lagrangian, and you know the corresponding term which is a total, which governs the total derivative obtained after you vary your action. What is important in this theorem is that the statement about symmetries has nothing to do with equations of motion. So first of all, you have to verify that there are transformations which leave your action invariant up to the boundary term. And if this is the case, then you can use your Noether theorem to write down explicitly an expression for the corresponding conserved current. And now I will show you that this local conservation law, which is expressed as a statement about the vanishing of the derivative of this local current, can be translated to the statement that there exist quantities which do not depend on time during the dynamical evolution of the system. So basically, I want to explain why this local statement here results in the existence of quantities which do not depend on time. So these quantities are now defined in the following way. You take the zero component of the current, which corresponds, zero direction corresponds to time direction. I take zero's component of the current, and I integrate it over special directions like this. And then my statement is, and so you assume that you have some hypersurface that denoted by B, which is in a sense orthogonal to the time direction. And if you take an integral over this hypersurface of the zeroth component of the current with an index n, and you assume that all the fields vanish at this special infinity, so fields tends to 0 when you go to special infinity, then the statement is that these quantities do not depend on time. Explicitly means that time derivative of Jn is equal to 0. And this follows precisely from this differential conservation law in the following manner. So you will get an integral over b dx djn0 over dt. But then you write down explicitly this conservation law here. This is d over dt g0n minus d over dxi gni, so equals to 0. So you can replace the time derivative of zeroth component of the current where the remaining components, and so you get here minus, no, plus, why I'm writing minus, sorry, it's plus here. It's minus integral dx b dji over dxi. So you get an integral of the total derivative, and if fields all vanish at infinity, well, you get, first of all, an integral over the boundary of this hypersurface B, which actually tends to infinity, and so this is by Gauss-Strogarsky theorem is a flux through the boundary of dB at infinity, and if fields vanish at infinity, then this integral vanishes. And this shows that you indeed find the corresponding conservation law. Okay, so this is a way how the Noether theorem is proved in the full generality with a non-trivial boundary term, which you can have after you vary your action. Any questions?
It's been bothering me all the time. The theorem was discovered relatively late. It could have been discovered, I don't know, 50 years before. What's your opinion? Why?
It's difficult to say. I'm not
it
quite
wasn't
sure.
Discovered relatively late, right?
It's late. To me, it's also late. All these conservation laws has been known, and the fact that they are related with symmetries
have been around for quite a while.
Absolutely, yes. I'm also wondering why it is the case. Only in 1918, the theorem was formulated as we know it now. I think it was originated from the discussion of Emmy Noether with Klein. Yeah. And somehow he triggered her interest to this subject. And eventually, yes, it's resulted in this beautiful formulation. So the conservation laws were around long time before, but such a precise mathematical formulation and this derivation really belongs to Noether.
Yeah, and the funny thing, it was done by mathematicians, not by physicists.
Exactly. Yes. And there is also a funny story how people discovered this appearance of this boundary term. So the action is not required, strictly speaking, to be exactly invariant, but only invariant up to this boundary term. So people try to check the invariance of the Maxwell equations with respect to conformal transformations. And there they saw, and this is a way how Bessel-Hagen actually found this term, they saw that in some cases there could be some boundary terms appearing and so on, and he starts working out and investigates this issue, and then he found that it's possible to have it there. And such terms typically appear when you talk, for instance, about Beres-T symmetry or supersymmetry. You always get the invariance of the action only up to some boundary term. And this is the answer to probably your question, the importance of the boundary terms. They could be there, but they don't spoil the main statement of the Noether theorem.
And when the second Noether's theorem here?
Second Noether theorem deals with local symmetries, and this is another interesting topic where you allow these parameters epsilon n to be actually space-time dependent. And this is a subject about local symmetries and about, or if you wish, about so-called gauge symmetries. And there is a famous second Noether theorem, which tells you that if you have such a symmetry with respect to local transformations, you don't really have the conservation loss. There are no new conservation loss, or no conservation loss at all, if you wish. No conservation loss. But instead, there are differential relations between equations of motion. Not all equations of motion are independent, but there are differential relations between them, like, for instance, Bianchi identities. And this is related precisely to the subject of the second Noether theorem. But possibly we come to this in the next lectures. Yeah.
How important was it that the Lagrangian depend only on the field on the first derivative? What happened if you had second derivative?
You could extend. Actually, in the original Noether theorem, she considered, she did not restrict herself to the first derivative only. In her formulation, you can allow any number of derivatives, it will work. There is no problem.
For the jet space.
Jet space, yes, indeed. You introduce jet space and then you extend all this discussion to this jet space. And yeah, it goes. It goes. So it's not important.
Could you somehow drop out the condition of vanishing of fields on infinity? For example, we are usually interested in the such solution which are not vanishing on infinity.
You can drop this condition. What you will still get local conservation loss, but you don't get the global one. This one.
What do you mean by local?
Local, I mean this.
Yeah, that's for sure.
That's you will have. Yeah.
So you have to say that for a solution that don't vanish in infinity, we would not have charge.
You will not have charge. That's true. So existence of the charge is related to the boundary conditions, and if your boundary conditions is chosen not properly, they will break the statement about conservation. You should always have this in mind. This is a very important question. Thank you. Thank you. In many cases, people just do not care about this, but in fact, you should care. You have a global charge defined as the integral of the hypersurface.
What we should care about?
Boundary conditions. Your fields here must vanish at infinity. Or for instance, in many situations, you deal with fields defined on a compact space-time, for instance, on a circle, or on the interval. And if, for instance, the boundary conditions are not such that this integral vanishes here, then of course you don't have a conservation law for this reason, global conservation law. That differential equations you always have, this differential condition you always have, local, but global not always. Any questions, any further questions? Yeah.
One more question, please. If we just consider these space-time variables like manifold, so can Noether theorem be proved in a similar way?
Here, actually, I don't. Well, yes, of course, yes, sure. Sure, you can consider a generic situation where your space-time is not really Minkowski space, as will always. Actually, this will not always be the case in my lectures as well. You can consider a more general situation where your quantum fields or classical fields are defined on a curved manifold with a non-trivial metric, not the Minkowski one. And then you have, of course, to modify the corresponding derivation, but you can derive the conservation loss. There is no problem. Yeah. Let me see. At a certain point, we have to make a break, or we continue till the end of the lecture, or what is it? I can continue.
It's up to you.
The more I talk,
Sorry.
the more information I will give.
Yeah. So please ask people. Officially,
If you would like a break, we can
after
have a
you
break.
talk.
No problem. No? Should we vote? We continue? Or we make a break?
People are young and strong enough. You know.
People strong, okay. Let me give you one example. It might seem a little bit abstract, this expression here. Well, you need to know what is phi capital, what is x capital. It looks pretty abstract. Let me show you that this expression contains our standard conservation laws, which we know, namely conservation of energy and momentum. Let me show you that this is indeed the case. Let's start from the simple situation where we assume that our action is invariant with respect to constant shifts of coordinates x mu. So actually, I will write this as an epsilon. Epsilon mu are parameters of our transformation, and we just assume that there is a translational invariance of our system. So our system is such that it's translationally invariant. So this expression here, so I'm transforming for the moment only coordinates, I'm not touching fields. So this means that I can write this expression in the following way. I can write, well, we know that according to our derivation, I should represent this equation here as x capital mu n epsilon n. So I have to understand what is this index n here. But it's very easy to see that this is something which can be written in a way epsilon mu nu epsilon nu, and therefore where index mu has the same meaning as n. And delta mu is a Kronecker delta. And this is something which is now becomes this x capital mu mu. Let's write it this way. And since I'm not transforming fields, this yeah. At a certain point, I have to identify the nature of the field I'm talking about. So I would like to compute the corresponding Noether current. I would like to compute it for the case of a scalar field. Take a scalar field, single scalar field. And a scalar field is an object which, by definition of what we call scalar, is an object which under coordinate transformations transform in the following way. Phi prime on x prime is equal to phi on x. In general, and in our lectures here, we will be dealing with a general case of tensor fields. So tensor fields in general, these are objects which might carry a certain number of indices, upper indices, say mu1 and so on, mu n, and a certain number of low indices, mu1 and so on, mu m. And then under general coordinate transformations, tensor fields are the objects which transform in the following way. dx prime mu1 dx prime mu n over dx alpha 1 alpha n dx prime mu1 d over dx prime mu m x beta 1 x beta m multiplied by phi mu1 sorry alpha 1 and so on alpha m beta 1 and so on beta m on the point x. So these are tensor fields. Objects with one index up, like this, phi mu on x. Transforming in this way is called vector. Thank you. This is a vector. And the object with one index down is called covector. An object with two indices down and symmetric and mu and nu. It's a symmetric tensor of the second round. It has the same transformation law as, for instance, symmetric of the space-time. So this is would be an object which transforms in the same way as electric. And maybe you know also what would be the transformation law for this object. Mu nu, one index up, one index down, like vector and covector. The transformation law here for vector covector together, linear operator. Transformation law for linear operator. It's like a matrix. Matrix indices mu nu, one up and one down. Good. So scalar is the simplest example, simplest possible example of a tensor. The guy which carries no indices at all, and then according to this transformation law, there are no derivatives here, and simply you have phi prime and x prime is equal to phi and x. This is what we call scalar field in theoretical physics. Okay, so for the scalar field, since the variation in the Denotes theorem is defined as a difference between phi prime and x prime and phi and x, and for the scalar field it simply vanishes. Therefore, this phi capital In vanishes as well for a scalar field. So we have only matrix, we have only this element x, but we don't have phi. And therefore we can straightforwardly write down an expression for the corresponding current. So in this situation, index n, I told you, has the same meaning, in fact, as an index mu. They are on equal footing. And in this case, the current which we obtain, I denoted by letter t. So this is the same, or this is analog of what I call g mu n. But now this index n is replaced by nu. According to this formula here, this becomes, and I think I also change an overall sign. So I'm not changing an overall sign, I'm just using this expression. This term is absent in our case, and I get minus gives me plus. And so as a result, I get the following expression. d mu phi, d nu phi, minus delta mu nu multiplied by original Lagrangian mass. This is how this current T mu nu looks like. And the conservation law, which we expect to take place from the Denotes theorem, looks like this for any nu running through the indices 0, 1 up to d minus 1. What is this object here? Stress energy tensor. Stress energy tensor. So this is how stress energy tensor for a scalar field looks like. Stress energy tensor.
There's of course an alternative school which call it energy momentum tensor.
Energy momentum tensor. And actually in my lecture notes I write canonical stress energy tensor or canonical energy momentum tensor. So you can read this in my lecture notes. Thank you for your remark. You are very straight to the definitions.
Stress or strength?
Strength.
Strength, not stress.
Yeah. No.
It's
Here is
stress.
Stress. Energy. Simply stress. Sometimes people call it simply stress tensor.
And I think there was a problem that
It produces a lot of stress for you when you learn it for the first time.
That's right. There was a problem that's not always symmetric in the indices.
I'm coming to that.
Excuse me.
I'm coming to that. Thank you for your remark. Yes. This is what is called canonical. This is what you immediately get if you apply this formula here. Yes. You see in this derivation already, from this derivation, you see that indices mu and nu are sort of on different footing. While one index is really responsible for taking this divergence, and the other one just enumerates how many symmetries you do have. This is shift of time, this is shift of space, directions, and so on. So indices mu and nu are on not on equal footing in general. Now, you can do similar derivation for the case of the vector field, vector or covector, but in that case you have to take into account that there will be a non-trivial function phi capital. In that case, you will get something here, something non-trivial here. Let me skip it. You can see it in my notes how this is done. Let me now maybe comment on the case of the angular momentum tensor, and this will be interesting, and this will allow me to talk about this question about symmetry of the stress tensor. Now, for the case of angular momentum tensor, to derive the corresponding quantity, I consider the transformations which are infinitesimal rotations of space-time, and these infinitesimal rotations of space-time, so infinitesimally delta x mu goes to x mu plus infinitesimal rotation, where rotation parameters epsilon mu nu form an antisymmetric matrix. So matrix which satisfies this condition here, and in that situation you can see that the variation of x, which is given by this expression here, epsilon lambda nu, it can be rewritten in the following way. It can be written as sum over independent transformation parameters, namely epsilon mu nu for mu less than nu, of x nu delta mu lambda minus x mu delta nu lambda epsilon mu nu. You see, the point is that in the Denotes theorem, you have to represent the variation of x as a variation which involves only independent parameters. But if I have an antisymmetric matrix, only its upper diagonal consists of independent variables. And this is a way how to write the variation. You can check that if you open everything up, then these two terms produce for you exactly the same expression due to antisymmetry of epsilon mu nu. And from here you can read that your object x capital now takes the form of having one index up as before, but now it has two indices down, and this indices mu and nu is a combined index for my previous index n. Because now you have many rotations. Yeah, if you have a d-dimensional space-time, how many rotations you can make in d dimensions? In general, d minus 1 over 2, right? And that's why now this index n runs d minus 1, d multiplied by d minus 1 over 2 values, and they are parameterized by indices mu and nu, now 2 by 2 indices mu and nu. And therefore, x is our matrix given by this expression here. Now you have just to plug it in here. For a scalar field, phi capital is still 0, and assuming that the action is invariant with respect to such space-time rotations, you will obtain the following expression for m lambda mu. And this quantity here, which is called, well, you will tell me how it's called. D mu phi x mu minus d mu phi x mu plus L x mu delta mu lambda minus x mu delta lambda mu. So this is a straightforward application of the Denotes theorem. What I have done, I just take this x capital here, these two indices mu and nu, plug in this expression, and the second term with Lagrangian originates from this term here. I assume that the action is exactly invariant, so there is no boundary term. And I'm getting a tensor which is called a tensor of angular momentum. That is what we call tensor of angular momentum. And as before, for the stress tensor, this guy is explicitly conserved due to the Denotes theorem, which means that its divergence equals to 0 on equations of motion. If equations of motion are satisfied, then the divergence of this object is equal to 0. Now, if you look at this expression for this tensor, you can see that if you combine this expression here with the derived expression for the stress tensor, then you see that this expression for the angular momentum tensor can be written in a very simple way. We are stress tensor as x nu t lambda mu minus x mu t lambda mu. So what you need to isolate one term here, this guy here, and the other one which contains x nu, and these two together give you one copy of t, and this term here together with this one gives you another copy of t. And so you end up with this expression here. Very good. So in fact, you build up the next conserved, local conserved quantity, the next integral of motion, by knowing only the stress tensor. And let me see. Let me see. Now, what I will do, I will not do the derivation, but I will just make a statement that if you repeat absolutely the same computation for the vector field, then for the vector field, say phi is an index lambda, for the stress tensor, you will find absolutely the same expression as before for a scalar field, with just only one difference. Here there will be index lambda over which you will sum. Otherwise, the expression will be completely the same. And for the angular momentum tensor, although you will get a bit different expression, which still can be written with the help of that stress energy tensor, and explicitly for vector, it will look like m lambda mu nu is equal to x nu t lambda mu minus x mu t lambda mu. So far is the same, but then you will find out an additional term which will look like d lambda phi nu minus derivative of the Lagrangian with respect to lambda phi nu phi nu. An expression which is explicitly antisymmetric with respect to the indices mu and nu. So this is an addition to angular momentum tensor related to the fact that you are dealing with vector. And now, if you would like to verify the conservation of this tensor, so if you would compute derivative d lambda m lambda mu nu, first you have to compute the derivative of this expression here, and you see that if you differentiate this expression over lambda, once lambda can act on the stress tensor, and the corresponding derivative will vanish because stress tensor is conserved, according to our discussion, it's conserved by itself. But that can happen, the derivative also act on axis. And when it acts on axis, you will get here, in one case, so you will get lambda becomes index mu and it gets down, so you will get t nu mu minus, and then when it acts on this x mu, you will get the metric t lambda mu, and index lambda gets down, you get t mu nu. So you get the difference between t mu nu and t nu mu. So stress tensor with indices transported. And from here you can conclude actually that if stress tensor is symmetric, if it is symmetric, so if this is equal to 0, then this piece here, addition to this term, is conserved by itself. It must conserve by itself if stress tensor is symmetric. And this expression here is typically known as a spin part. Spin part is something which corresponds to transformation properties of your object with respect to space-time transformations. For vector, it's one expression. For tensor, it's another one. For scalar, it's absent. So this object is related to spin. Spin of the field. It's also known under the name polarization tensor. Polarization tensor. And so in the case, if stress energy tensor is symmetric, then you get another interesting conserved quantity which is related to the spin of your field, related to the way your field transforms under space-time transformations. Now, we come to another interesting point here is how uniquely all these quantities are defined. For instance, how uniquely this expression here for the current is defined. It appears that in fact this is not this object is not uniquely defined in the sense that you can modify the expression for this current without spoiling the local and global conservation laws. And this is done in the following way, which is actually, this way it's done is called improvement procedure. And I will explain the word improvement in a second. Is it possible to form it? Although it's also, does not matter. Now it does not really matter. Okay. Improvement procedure. Improvement procedure is the following statement: that if you have a conserved current, that means the current which satisfies this equation here, then you can modify it by adding to it a total derivative, like d, which index I use. Let me see, the mu chi mu nu n, where chi is an arbitrary function of fields which is antisymmetric in this indices mu and nu. Then this conservation law will not be spoiled because you see, if you add on this addition, on this improvement term, with the derivative d mu, you will get 0 because derivatives commute and they are multiplied here, and these indices mu are paired with an indices of an antisymmetric object, and therefore you get 0. So the conservation law can be changed by adding up some function which is antisymmetric in the indices mu and nu. And sometimes it is possible to start from the canonical stress tensor. It might happen that this stress tensor is not symmetric, but there is a possibility to actually improve it in a way that it will become symmetric. That is not always possible, but sometimes it is possible to find such an improvement term that the stress tensor becomes symmetric. And when it is possible, and you know that you can change your T in such a way that it becomes symmetric, then my considerations here must apply, and I can conclude that in that case the spin part will be separately conserved. This is not always possible, as we will see later on, maybe tomorrow, that for instance for the Dirac field, for the Dirac particle, it is not possible to find out an improvement term such that the stress energy tensor becomes symmetric. And therefore for the Dirac field, the angular, the orbital part, this is called orbital part, and this is the spin part, orbital part, and the spin part. For the Dirac field, they do not separately conserve, and you can never improve the Dirac tensor in such a way that the orbital part becomes conserved. And so for the Dirac field, for instance, this is not conserved and this is not conserved, but when you add up them together in the total stress energy tensor, then it appears that it becomes a conserved quantity. For the Dirac field, this is
How to understand it in some simple finger manner? Is it possible, or it's just matter of fact?
Yeah. Spin is something non-relativistic. Let me put it this way. This is an explanation. If you would like to see spin, you should consider very slow moving electrons, and you can understand. Then there is a possibility for you to go in the rest frame of the electron, and then you are in the rest frame, and you get.
You can take massive vector field. What's the difference? You can go to the rest frame.
Yes, yes.
Very
For the case of the vector field, of massive vector field, the things are better because transformation laws are not of a spinor with respect to the Lorentz, but with respect to the with respect to the Lorentz, transformations are different. It's a vector field, and for that case, things become actually no. Even for the I think it's not related to the fact massive or massless. This has nothing to do with that. In fact, for the case of the vector field, in spite of the fact that you can separate the spin part from the orbital part, the notion of spin, strictly speaking, even for the electromagnetic field, does not exist. Because you can understand physical degrees of freedom of electromagnetic field only if you impose a gauge. So, for instance, you fix the Coulomb gauge. But the Coulomb gauge makes the transformation properties with respect to the Lorentz transformation to be related to those which are related to the, it makes them non-trivial, because now you impose an extra condition of your field, right? You impose, whatever you prefer. You can impose the Coulomb gauge, or you can impose the Lorentz gauge. In any case, what you do, you impose one condition on this index mu. Now, for instance, if you want to talk about this, this I don't want to discuss. I want to discuss only physical degrees of freedom. Then I go to the Coulomb gauge. I know that it's not gauge invariant condition, and that essentially means that I cannot so easily transform this index with respect to Lorentz transformations. Lorentz transformations are not compatible with the imposition of the Coulomb. So, if you want to understand what will be conserved here for the case of the vector field, let me just say right away that what you will see here is a conservation of helicity. Helicity is a quantity which will be conserved. helicity. The same for the Dirac field. Helicity is the right quantity to be conserved instead of spin, instead of what you call spin. Projection of the spin on the direction of motion. This is what is conserved for the case of the Dirac field. Helicity.
Just thinking in more general terms, should I imagine a homology theory that would or would not allow me to correct the geometric tensor to make it symmetric by those additions? What that homology theory is about?
Yeah, so I don't know exactly how to formulate it in terms of homology theory, but I can tell you exactly what is the condition for the stress energy to allow asymmetrization.
Local, of course.
Yeah, local, yeah, sure. All these functions which I'm adding are local. And the condition is the following, that if you are given some tensor, T mu, and you evaluate its antisymmetric part, then necessary and sufficient condition for this tensor to admit improvement to become symmetric is that the difference between T mu and T mu must be a total derivative, total divergence. So it must go like, it should be minus, or whatever, it should be like d rho on some omega rho mu nu. There should exist some omega rho mu nu such that this equation here is true. It must be total divergence. And actually, I was planning to solve today an exercise about this. If you take, for instance, a standard Maxwell action, and if you apply canonical procedure of deriving the conserved stress tensor for electromagnetic field, the expression which you will get will not be symmetric with respect to the change of indices mu and nu. But you can work out what is the difference, and you can see that you can always represent it in such a form. And if you know this function omega here, you can explicitly construct what you have to add to t to make it symmetric. And this addition is called Bell-Infante, or this tensor, which is symmetric and constructed from originally non-symmetric tensor, is called Bell-Infante tensor. And if you wish, I can give you this procedure explicitly. So let's see.
One more
Yeah.
question.
Sure.
We know that the energy momentum tensor has another capacity in gravity theory. So it's
In which series?
gravity theory.
Yes.
So it is derived as the functional derivative with respect to the
Yeah.
metric. And in this case, it's always symmetric.
Absolutely.
How it is connected with your arguments?
With my arguments,
So we can always get a symmetric
not
energy
always,
momentum.
not for the Dirac field.
Well,
for the Dirac field, if you think how Dirac Fermion interacts with
because
gravity,
you need field bias in this
Yes,
case. You
field bias is not
cannot work
symmetric.
with the metric. It's
Exactly,
not metric. It's
exactly.
something more.
exactly.
more
So for the
general.
Dirac field, you
This is
agree
the
with me?
problem, that's
Yes,
true.
yes.
But otherwise, you
uh,
should always give a symmetric.
Yes,
momentum
yes,
tensor.
and exactly. So in gravity, there is an extra way. Well, gravity gives you another way to define the stress energy tensor, and in that case, of course, it comes out symmetric. So what you have to do, you have to consider your theory on a non-trivial gravitational background. So you put non-trivial metric g mu, and you define now your Lagrangian to be a function of your fields, and in addition of the metric g mu. And you still define the action in the same way. It's an integral of the scalar field, which depends now on g mu and phi. And you can show that stress energy tensor then can be defined, which is symmetric one, can be defined in the following way. So 2 divided by square root minus square root of g, where g is the determinant of this non-trivial metric, variation of the action, or variation of the Lagrangian density with respect to the metric g mu. In that case, it comes out symmetric. Now, if you don't know anything about gravitational theory, and you are just in the framework of the Denotes theorem in the flat space-time, then, of course, you don't know. And for the Maxwell theory, the stress energy tensor will appear to be non-symmetric. The one which you derive from the gravity is symmetric. And the difference between them is precisely an improvement term you need to add. That's very simple. That is how it works. And so I was planning to make this exercise to show you explicitly that you can do that. You can find such a procedure. For the case of fermions, things are different because indeed, in order to couple fermions to gravity, you need to introduce field bind, and then of course things become different. Now, well, I think you get the basics of improvement, and we can discuss it for the case of the vector field or Maxwell field when it comes to the exercise class. Let me make just one or two maybe remarks. There is a further way of improvement of a symmetric tensor. Suppose your tensor is symmetric already, but you can still further modify it by adding to it such a thing. You can add to it d rho d sigma w mu rho nu sigma, where this function w mu rho nu sigma has the same symmetries as a Riemann tensor in gravity. So that means that it's antisymmetric with respect to the first pair of indices, and it's antisymmetric with respect to the second pair of indices. And it's symmetric if you commute these indices in pairs. Then you can see that this will not spoil the conservation law because of this symmetry property. So if you differentiate this with respect to d mu, it will vanish. So it will not spoil the conservation properties. But sometimes making such an extra addition, an extra improvement, this expression actually is symmetric in mu and nu. Making such an improvement, what you can reach the tracelessness of the stress tensor. So sometimes, by this improvement, you can make your stress energy tensor to be traceless, to satisfy this condition. And this is related, when this happens, this is related to the fact that sometimes, for particular theories, Poincaré invariance, which is an invariance with respect to shifts and with respect to Lorentz transformations, can be further extended to a bigger symmetry group, which is called conformal group. So the possibility to improve your tensor up to the point where its trace vanishes signals the appearance on conformal, so-called conformal symmetry. I'm not sure. I think I have to.
Is it equivalent that it can be done only for massless fields?
Yes. Yes.
Is it conformal or scaling?
If you require that this equation here holds at any space-time point locally, then this is conformal invariance. If you require that your integrated tensor trace vanishes, then this is scale invariance. Scale invariance is weaker. Conformal invariance is stronger. And I hope we will talk about conformal symmetries in the exercise class and maybe the next lecture. Thank you. I think that's it.
So, coffee break.